Welcome back, everybody. In the previous video, we worked with the bandpass filter. We learned how to implement it, and we saw how it changes the signal. Now in this video, we will talk about the Pan-Tompkins algorithm. It also has some filtering techniques, and it helps us detect R peaks. Now it has three main steps. The first step is to find the derivative of the signal data points. Step number 2 is to square the signal. And step number 3 is to implement the moving window. Now I will talk about each step in details. We will see how it's done mathematically, and we will also see how it changes the signal with each step. Now, first I want to show you how it's done mathematically. We will perform convolutional operation. It's nothing difficult, pretty simple math, but still I think it's worth knowing how it's done. Now, for example, we have our signal, and these are numbers. These numbers are just random. It's just an example. And let's say we have 10 data points, 0, 1, 2, 3, 4, so on. Now, we also have a kernel mask, which is usually the same. It has the same values, but sometimes it can be modified and changed to your own needs. But we will just work with the standard one, which looks like this: -1, -1, -2, 0, 1, and 2. Now then multiplied by 1/8, which is -0.125, -0.25, 0, 0.25, 0.125. So this is our kernel. Now to perform the convolutional operation, we just need to overlap the values in our kernel over the signal values. So we always target one value at a time in our signal. So it will also be it's always centered by the middle value in our kernel. So for example, 0 is our middle value, and let's say we want to perform the convolutional operation with number 5, with the index 6. So 0 will be overlapped over 5. -0.25 will be overlapped over 4, and -0.125 will be overlapped over 3. Now the same applies to the rest of the numbers in our kernel. Now the operation is pretty simple. What we need to do, we just multiply these values, sum with the next pair of values, sum with the next pair of values. So it'll look like this. Let's say this is our convolutional operation. It'll look like this: -0.125 multiplied by 3 plus -0.25 multiplied by 4 plus 0 multiplied by 5 plus 0.25 multiplied by 6 plus 0.125 multiplied by 7, which equals to 1. I'm not sure if I miscalculated here, but it doesn't matter. It's just an example to show how it's done. And so 1 is going to be our value after we apply the kernel to our 6th data point in the list. Now let's do this in the code. So let's write a function called derivative filter. frequency equals to 100. Now our kernel is equal to numpy.array -1, -2, 0, and 2 multiplied by 1/8. So this convolve will perform the convolutional operation that I just showed on the paper. Our ECG is signal and kernel. All right. Let's apply our filter. If you don't understand where this reshaped data comes from, please watch the first video. Frequency 100. Now let's plot the signal and see how it changed it. Now you can see what happens. Now it kind of reverses the R peaks, because when we perform the convolutional operation, the slopes that go up will go down and vice versa with the slopes that go down. Now we could also use just numpy function. We could just do it this way. For example, we have our reshaped data. So we can just go with pi.diff reshaped data. Oops. Now you see the result is pretty similar, but now there's no reverse effect. But I think it's still okay to use both of them. It's just you have more control over this function. But either way should be fine. Now step number 2 involves squaring the signal. So we can just do squared signal. Or I could just make it more simple. Just show you what it does. Just square it. Now this is the result. So let's still square the signal. Okay, and now we move into our third step, which will be a little bit more complicated, is where we need to move our integration window. So we'll write a function moving window. For signal, frequencies 100, and the window size in milliseconds is going to be 150 milliseconds. Window size window milliseconds divided by number of points, which is 1000 in our case, multiplied by frequency. So 150 divided by 1000, and then multiplied, well, it looks like this. 150 divided by 1000, and then multiplied by 100 is going to be 15, which is 15 data points. So our window size is going to be 15 data points. Window size divided by window size. So what it'll do, it'll just, and then we will also perform the convolution operation where we have our NP convolve. Our signal will be overlapped by our window values. So it'll just kind of flatten these sharp R picks. Let's see what it does. Window. Squared signal. Oh. Okay, typo. All typos. Now let's see. Yeah, now you can see our picks that were sharp now kind of flattened out now, and we can do the final piece, which is the actual detection of these R picks. Now let's create a new function called manual QRS peaks. Just manual R peaks. Signal frequency will be 100. So first we need to have a threshold. I'll explain what it means. Divided by 2. So first we have our NP mean, which is going to be the value, the average value of our data points. So for example, our data points are 1, 2, and 3. So NP mean is just going to be 1 plus 2 plus 3 divided by 3. Yeah. Plus 3 divided by 3. This is going to be our threshold, meaning that if it's above the threshold, it can look for the R peaks over that threshold. Now minimal distance. Minimal distance, it's also like a threshold. Here it's 200 milliseconds. in samples. That means that if it's below this, maybe there's some noise and there's some other peak or spike in the signal which is not an R peak, it will skip that because there's a minimal distance between these two R peaks, and everything below that will be ignored. So we don't, this way we can avoid some unwanted R peak detections. Next we will store our peaks here and the length of our signal is just signal for I in range 1. So we'll loop through each data point in this range of our signal range. So if ECG, no, if signal at index I is higher than signal index I minus 1 and signal at index I is higher than signal at index I plus 1. I'll explain what it does. And signal at index I is also higher than the threshold that we specified earlier, that the frequency threshold. Yes, so for example, everything above this can be considered as an R peak, and everything below this threshold can be detected. Threshold. So quick explanation of what it does. It will look for the highest number between two neighboring values. So for example, again, our signal looks like this: 0, 1, 2, 3, 4, 5. Okay, and let's say we're working with this value. So it will look for the neighboring at the neighboring values. So the neighboring values are 2, 3, and 4. It needs to be higher than both neighboring values. So maybe let me put another 1, 2 here. So R3, well, actually, let me change it. Maybe 1, 1, 2, 2. Then boom, we have our R peak. Okay, so 6 is the spike, is the highest value. So it'll first look whether this 6 is bigger than this number, and it'll look whether this 6 is bigger than this value. So if it is, that means that there is a spike there. Therefore, this will be considered as an R peak spike. So if it satisfies this statement, then we just peaks that append our value at that index. Turn, change it to an NumPy array peaks. Okay. Now let's try to apply this function. Manual. Art peaks. What was our last window signal? Oh, yeah. All right. Now let's take a look at the detected R peaks. So we'll change one small part here. Remove this. We will display them as lines. Could do that. We have our peaks. Color red. Okay. Let's zoom in. Okay. So it does make some mistakes. So for the sake of this video, I think it's fine because we could alter our settings in our functions and see if it helps. Because as you can see, it sometimes detects 2 R peaks in one signal spike. Maybe there's a threshold issue or the distance issue, but I think we can just ignore this problem for now and see what it looks like. So you can see here 33, 36 is probably these 2 R peaks. There's a mistake. It shouldn't be like this. Let's say maybe it should be just 33, but apart from them, and another mistake here, 868, 878, and maybe this one too, but again, it's okay for now because in the next video we will use the NeuroKit library, NeuroKit 2 library, which is really good and accurate with detecting R peaks. It doesn't only use Pan-Tompkins algorithm, it uses a few other algorithms for R peak detection. It also uses some correction algorithms to avoid things like we are facing right now. Therefore, it's really accurate and good at detecting R peaks. And after that, we could also see how we could utilize our extracted R peaks. So this is it for this video, and I'll see you in the next one.